Hey guys, it's Oshibi. Wanted to make a quick video on showcasing this program that I developed over the past couple months. It's called GenPass. It's a password generator that randomly generates a string based on the length that you set. So real quickly, we can actually show the files in our directory here. You can see that I have this binary called GenPass, and there's also a couple of other programs that we're going to go over later inside of here, or a couple other binaries really. Those aren't actually important to GenPass, but they are important to analyzing the efficiency and the how do you say, stress testing the program. So without further ado, let's actually take a look at how GenPass works. To run GenPass, we simply just invoke the binary or execute the binary, and we'll pass the argument -h, which will show us the help menu. If we just load it normally, it'll also show us the help menu, but it's typically better just to pass h when you're learning a new command. So yeah, we'll just keep it at -h for now. As you can see here, there's a couple of different arguments that you can pass through it, but the main one that we want to invoke is -l. -l actually sets the length that your password will be generated in, or well, sets the length of the password, right? So if I were to say, okay, I want a password with no spaces, but I want it to be a length of 40, it'll give me a 40 length password with these characters, random characters. And each time that I call this, you can see that it's a random string each time. I could also say, hey, I want only numbers, and it will do the exact same thing, but with numbers. Taking a look at what's happening under the hood, we could say, let's be verbose in our command, but also let's say, hey, I only want, let's do a mix of upper and lowercase letters. So you could see here that it loads all the capital letters inside of this buffer here, but it also loads all the lowercase letters inside of the buffer. And it generates the seed, and it generates this matrix down here, and it tells us which iteration of this matrix is actually showing us, and it also tells us what the random number modifier is. So because we have 26 letters in our English alphabet, and well, there's two sets of the English alphabet that we're loading, uppercase and lowercase, there's a total of 52 characters that we need to randomly generate. Down here, we can actually see what the string was actually truncated down to from this matrix. It actually goes line by line and then combines it all into one. And we can also see that there's another string, which is the exact same thing right here. This is, in the program, actually a standard error message. It's just a logging message that the program does, so that you can actually pipe, let's say I want the same thing, but pipe that over to a text file, and you can see that this password doesn't actually appear a second time. But if I were to read out that text file that I just made, it's right here. So without further ado, let's actually take a look at what's happening underneath all of this. So really briefly, I really want to go over what the ASCII table is. If you don't know what ASCII is, ASCII is an abbreviation of the American Standard Code for Information Exchange. Since computers only can understand numbers, ASCII was developed as a way for computers to register characters as numbers, right? This is actually really important in C when it comes to how we generate this matrix of characters. But more importantly, the only reason why I used ASCII in this program overall, since it actually got superseded by Unicode and UTF-8, is because, well, not all password logins accept special characters, right? And if we're not going to be using special characters all the time, well, we might as well pick the path of least resistance, right? So why put extra work on us when we can just simply use ASCII? So the way my program actually loads ASCII is very, very unique in the sense that, well, it's not unique as in it hasn't been done before, but the way that these arguments are actually called, for example, if we wanted with no spaces, uppercase, lowercase, etc., it actually sets the struct variable to what the character set is going to be. And that's actually done at line 200. We can see, actually not line 200, I'm sorry. At line 109, inside of this variable here, where we're actually past the argument of char set. And we'll cover how this all comes together later on in the video, but basically how the ASCII is loaded into our program is that we have a minimum variable defined as x inside of here. In the case where we're doing, genpass L32, we could see that, actually, sorry, you have to pass the verbose option here. Forgot to do that. We could see that at values 32 through 126, we're actually loading that into this buffer here. And that buffer is actually defined in the struct up here, ASCII. Underneath seeds, it's defined as ASCII. But if you notice, like, inside of this function here, we're not actually calling or loading up that buffer quite yet. In fact, we're actually loading arguments to pass into the buffer. But you might have noticed that this hasn't been passed in. We'll cover why this actually isn't passed into here yet. But we can see that it's a switch case function that sets the minimum variable, minimum value for loading the buffer. So if we actually look at how the buffer's actually loaded here, we first actually go through this another switch case argument, which is where that other variable comes into play, args.ull. You can see here that this is the max value, 127, inside of our for loop that we're setting, which is down here. In the case of a length of 32, VL32, we actually start at the character 32 all the way up to 126. So here, the integer I is actually set to 32. It only will loop up to 127. So in this case, it will only loop up to 126. It checks if I is less than 127, I should rather say. And then each time it iterates, I is added, 1 is added to I. But inside of this loop function, you might have noticed that there's actually another switch case statement where it checks the variable C. And C is actually defined up here. What's important about this variable is that in the cases where we're not having to loop again for certain characters, we're just actually loading it all into the buffer at once, right? So more accurately, the only time that this function down here will ever repeat itself is if we're loading upper and lowercase letters with the argument -m. And that's because, well, if you look at the ASCII table here, the lowercase letters in ASCII are actually 32 numbers away from the uppercase letters. So uppercase A is at value 65, but for lowercase it's at 97. So we have to account for the 32 characters in between, which actually is accounted for at the end of the loop, right? So each time that this loop happens, we can see that if we go back here, let's say I want upper and lowercase letters, but the length of 32. We could see here that all the capital letters are actually loaded in first, and all the lowercase letters are subsequently loaded in. And that's because it actually checks inside of the loop function here, hey, are we repeating again? But if I were to, say I want numbers only, it's going to say, okay, well, the max is 57. We're only going to have to loop through this once. We're not going to go back and load unnecessary ASCII values or have to change an offset. And that offset is actually done inside of the loop here as well. So now that we covered how ASCII is loaded into our program, I really wanted to quickly go over pseudorandomness and how dangerous pseudorandom number generators can actually be. Once we get into the main algorithm here, we actually have to seed a pseudorandom number generator, right? And when it comes to sensitive information such as passwords, it actually can be very dangerous using a random number generator. It's dangerous because you can create race conditions where, let's say you run the program at, let's say that we seed the time into the random number generator, right? If you seed the time, if this program is running at the exact same time as another instance of the program, you can actually generate the same exact password. When I was first developing this program, that actually became a very big issue because it would not only, as I was generating these passwords, would the bit entropy go down, but also it's a risk, right? Because if you run this at the same time, let's say an attacker is trying to break into, and he knows that you're using this password generator, he can generate the exact same password as you. And I actually found ways to mitigate race conditions inside of the password generating algorithm. But a big reason why this is a very dangerous attack vector is because numbers are technically not random when it comes to computers. A famous quote from John von Neumann, a renowned computer scientist and one of foundational thinkers of computational science. He's been quoted to say, anyone who considers arithmetical methods of producing random digits is, of course, in a state of sin. And that's because computers don't actually generate random numbers. It's set in an algorithm that actually can be broken from time to time. So that creates an attack vector that we have to worry about when generating passwords. And moreover, what's more important to password security is actually the entropy of the passwords, right? And what entropy basically is how easy is it for a computer to randomly guess your password from a select string of characters, right? And how entropy is actually calculated is you take the amount of characters that you have. In this case, we'll define it as C. We're going to make some space here first. So you have the variable c, right? And this is the amount of characters that you're using. Not only that, but you also need to consider the length of your password, right? So in this case, we'll assign the variable n to length. And how you calculate entropy is you take the amount of characters. In our case, since we're using the ASCII table of values 32 to 126, we have the variable c is actually equivalent to 96. And the length of the password is equivalent to whatever the user defines, right? So, for example, we'll just use the number 8. So to calculate entropy, you're actually setting 96 to the power of 8. And then to calculate bit entropy, since we're doing it at a computer, which favors base 2, which is binary, we're actually doing the log of 2 of 96 to the power of 8. Let's take an example of this real quick in our password generator, right? Let's use the number 32, because 32 is my favorite number for this video. Since we have 94 characters inside of GenPass that we can ideally use, we can actually calculate how much entropy this was going to be. Ideally, this will come out to have 208 bits of entropy, but through further testing, and actually we'll showcase the script here, I actually wrote a script to run this program like 1,000 times. You can see here GenPass L32, and it actually tells us the entropy through keepsx's command line utility. If we actually run this script, estimate entropy, give it a moment. And then I also have a average calculator in here as well. Calculate average, and then pass in the data set. We actually get an average of 190, which is about 9.1% weaker than the ideal entropy that we should get. But we have to account that the numbers aren't actually truly randomly generated, right? So in our case, this is actually a very strong password. There's another video that I'll probably link down below going further into what bit entropy is and how long it actually takes to crack passwords if you're interested in looking into that. But now that we covered what bit entropy is, we can talk about how this actually all comes together, and what this matrix really is. So basically how it works is that the program has a predefined set of rows and columns that we can actually see up here. We define the rows by 8 and columns by 8, and that actually sets the matrix size for our string generator here. It actually does a quick pass through to see how many times it should iterate itself. But for each iteration, a new seed is generated based on 3 values, right? The current time multiplied by the process ID plus the previous seed times the iterations. Since we're only running the program in here only once, we're actually not using the previous seed. For the next generation, however, if I were to, let's say, generate a password of length 128, we could see that we actually generate a new seed to feed into the matrix. But what happens inside is the matrix is generated, it seeds the new seed back into itself, and then it generates a new seed for the matrix to actually generate. So each part of the matrix or value within the matrix is actually loaded with this function right here, or this block of code right here. Int z equals random modulus args.mmod. If you remember from the beginning of the video, there's inside of the specific arguments in the main function, this is actually defined down there. That's because, well, if we're using a specific character set, right? For example, if we're using numbers, there's only 10 digits that we can really go through. But if we're doing something large, like, you know, the entire ASCII table of printable characters, well, that's going to be 94, so it's not going to include everything inside of the buffer. So we actually use this variable in the next line here to actually load the matrix full of the random characters chosen from this seed here. And then there's a couple lines just to, you know, print out what's happening using the verbosity argument. But we actually then truncate down the matrix down to a string. We do this by going through each and every part of the matrix and then setting this struct variable string.betterString down to what the matrix prints out. And a big thing that I kind of left out on how this actually all comes together is actually through the perfectly named function sandwich. So here it breaks down what's happening step by step, right? So we first initialize a matrix for integer values, and we set the rows and columns and by 8, because that's what these are assigned to. And then we load the ASCII table into the we load the buffer, right? That's what's happening here, ASCII load. And then we actually generate the string here, and then we print out what the better string is, or, well, the actual string that is generated. Here's just the help command. We can really ignore that. But so you might be asking yourself, why use a matrix at all if you were just truncating it down to a string, right? And the main reason we use a matrix in this program specifically is, well, it's actually increasing the bit entropy. I actually tried to load it directly into a string before I actually experimented and was like, okay, what if I tried loading into a matrix and truncating it down? And I found that I actually increased my bit entropy of my passwords by using a matrix rather than a string directly. Because, well, if you really think about it, when you're loading the values inside of this matrix here, it's a random number each time, right? Like, it's not going to be the same exact letter. Like, when I was doing it directly to a string, it was giving me the exact same letter each time. And I was like, well, this is not good for passwords. Because if you have a password of, let's say, QQQQQ, that's not going to be as strong as bracket GQ $Y hashtag PF, right? So ideally, this is actually contributing to the bit entropy. If I had a larger matrix table to work with, it probably would generate a much stronger password, but I decided to go with an 8x8 solution, not only because it fits perfectly into 256, but also because, well, mathematics and computing, right? 8 is a power of 2. But also, keep in mind that using a matrix is actually a lot more optimized for a computer than using loading a string directly, right? That's because of how for loops actually interact with memory. If you're interested in that, I'll leave a white paper down below further describing how matrices are used in memory optimizations. But furthermore, I actually also tested what it would be like using smaller matrices, and I found that I had the same issue as loading it directly into a string, which was I was getting lower entropy each time I would run the program. Additionally, when it comes to seeding the random number, I actually use the amount of iterations that this has gone through as one of the factors within the function itself, right? So, for example, like iteration 4, iteration 3, iteration 2, iteration 1, if we look at what's happening inside of the function here, it's actually multiplying it by that iteration, right? Because z is the amount of iterations that the program is actually doing. So it's counting each time times 1, times 2, times 3. Okay, well, what does that do for seed.newSeed? Well, it creates a completely random new seed each time. So that was one way I actually mitigated race conditions inside of this program. Another thing you might have noticed is that I actually used the process ID, which is also quite random in itself. And I multiplied that by the time that you're running the program. So yeah, this was GenPass. If you found it interesting, or if you want to mess around with it, I'll leave a link to the GitHub repository down below. Thank you guys for watching. This actually took way longer than I expected it to take to film and get out there. But yeah, if you're interested in this kind of content, leave a comment down below or like the video, and I'll try to make more content about programming. So yeah, hope you enjoyed. Thank you for watching once again, and have a good rest of your day.